recording. No, it's not funny. You're laughing. It was not funny. I had many classes and I was struggling to talk and to hear my students. Anyway, now I would want to ask you to put your cameras on if you can for at least the first 10 minutes, please, because I would be happy to see you. This is one. Two, before I tackle Marilene's question, I just want to inform you that I'm practically done with correcting lab 1. I still have half of your class only, so hopefully you will receive the corrections today. All right. Yes, let's start with questions about lab number 2. So the first question is, Marilyn, can you please explain in report 2 how we calculate uncertainty on a theoretical acceleration? Yes, I'm gonna do this. Next, I have a quick question about alpha RMS. Do we do sigma over radical n? So we do sigma over radical n. I'm thinking, what is S? I think if you do S over radical n minus 1, don't you get the same answer? I don't know, Rita, you confused me. Because on your calculator, what does S stand for? Did you try both? Listen, I'm gonna take note of it and try both. And I have a calculator that would give me sigma and delta. Just a second. I have a checklist for this evening. Let me keep it here. Sample standard deviation. Yeah, I know for a fact, theoretically, that it's sigma over radical n. And I'm gonna write it in the chat. So it is sigma, which is the standard deviation, divided by radical n, divided by square root of n. This is a fact. But now on your calculator, you have S and you have delta. So which is which? I want to make sure. All right. S is the estimated value for the sample. I will get back to you. Let me write your name, Jana, right? No, not Jana. Who's asking? Rita is asking. How about I send an email for everyone? All right, I'm going to send an email for everyone discussing what's on the calculator. We know for a fact it's standard deviation over radical n. Now the question, your calculators, you have something called delta and something called S. In some calculators, you have delta n and delta n minus 1. These are the old Casio. So let me see what's on mine. Probably I can check now. On this calculator that I have here, I have whatever values, and then shift 1, variable, I have delta and S. I think I used to do S over radical n, but let me check if the answer makes sense. I would send you a screenshot probably on the chat as well so other sections can see it. All right, so I'm gonna get back to you for the standard deviation. All right, now let's open a slide, any empty slide to discuss the acceleration for this one. All right, so 10 acceleration is equal to g sine theta. And the question is, how do I find the uncertainty on the theoretical acceleration? The uncertainty on A is equal to derivative of A with respect to g times alpha g. All of this squared. My handwriting is not that awful, it's only my trackpad. dA, derivative of A with respect to theta, then uncertainty on theta. And all of this is squared, all right? And we can do the radical. Now you have to, we know G, it's 9.8 plus or minus 0.1. So G is given to be 9.8 plus or minus 0.1, and the unit is meter per second squared. Okay, theta is given to you and the uncertainty is given to you as well. Make sure you convert the uncertainty to radians because it's alone and degrees is not considered to be SI unit. All right, when you have sine theta or cosine theta, it's okay to keep theta in degrees because it's under the umbrella of the function sine or cosine. So it will not have any unit after you do the function. But alone, it cannot stay in degrees. Now for the derivative, you help me. What is the derivative of A with respect to G? What is it equal to? Yes, so my question again is, what is the derivative of A with respect to G? Yes, G is my X and sine theta is the constant. So sine theta is the answer. Now, what is the derivative of A with respect to theta? So it's like I have G sine X. What's the derivative? It's gonna be G cosine X. Very simple. Now plug in all the values. Don't forget to do the radical. And then 3-point system. Make sure your uncertainty is one significant figure. Don't forget to add a unit and make sure to round your value according to the uncertainty, okay? Like if the uncertainty is 2 decimals, the theoretical acceleration should be 2 decimals as well. Yeah, did I answer your question, Marilyn? All right. Now I'm gonna ask everybody else any question related to lab 2. When calculating the A theoretical, yes, Kausar, what's wrong? How many decimals we take? It depends on A. Let me open a new slide. I'm glad we can do this anytime we want. All right. So let's say the uncertainty on A is 0.02. Don't forget to round to one significant figure, meter per second squared. And let's say that A is 2.425 meter per second squared. How do you round, Kausar? And that's an example that may not be applicable to our lab.
2.42.
So we look at the error. The error is 2 decimals. So this should be 2 decimals as well. So 2.42 is the one that we're gonna take. No need to round up because 2 is an even number. So we keep it as is. If you wanna round up, we're not gonna fight over this. Did I answer? Yeah.
No, my question is when I calculate the theoretical, and first before calculating the uncertainty, does it matter how many decimals do I take? And I know I will adjust my answer according to the uncertainty after I calculate it.
And you have no choice.
At first, does it matter?
And you have no choice because I will see your final report. I cannot see what you did first and then second. So you're gonna calculate, then do the uncertainty, then move up. You have a lab report that is typed, no need for TPEX. You fix it. All right. Yeah.
Thank you.
All right. Why dA over dG is sine theta? This is a very good question, actually. Let me use blue. All right. G is the x, is your variable. So this can be written as x times sine theta. And remember that sine theta is a constant. Your only variable is x. So this is very similar to constant times x. The derivative of constant times x is constant. In this case, this is your constant. All right? Yes. So Maria, when you take G to be your variable, the other guy should be a constant. When you take theta to be your variable, G is going to be the constant, and this is going to be sine x, the derivative of which is going to be cosine. All right? I don't want you to freak out when you see derivatives that are a bit tough. Remember, we're doing 10 labs only, and you will end up doing 10 different derivatives. So بتحفظون، مش رح يجي شيء من المريخ، هول 10 رح يجوا. Right? So for each lab, you will study the derivative needed, and that's it. And I will tell you what it is. Right? Remember, we're not doing math, so don't get frustrated. Let me help you on this level. More questions related to lab 2. So I'm done with this. Now we're doing that. What should we talk about in question 9 comparing, I don't know who. All right, I'm gonna open question 9. By the way, I have it open. The manual, I mean. Which side needs a greater inclination? All right, so the wooden surface and the textile surface, one of those surfaces would need a greater angle for motion to happen. So which side needs a greater angle? The answer is wooden surface or textile surface. Why? Because, I don't know, because basically you have the values. If you want, you can discuss a bit friction. You can say the wooden surface has a smaller coefficient or a bigger coefficient of static friction, which means it would be more difficult, or we need a greater inclination to reach the threshold of motion. Write something about it. So include friction, because otherwise the question is very lame. So discuss friction. Yeah, I think this is what they meant. Who wrote this question? Not me. I can't remember writing this question myself. Yeah. But anyway, I think whatever you answer would be okay. Fine. Ya Allah, they're fixing their house again. All right. Hopefully it's not going to be intense. More questions concerning lab 2. That's it. I can see you're doing okay. By the way, I need to confess something. Last week, when we had our live session, I was a bit careful with you because I realized that you have a lot of gaps, and I felt a little bit guilty and bad because you missed 2 sessions in a row. One session because Tuesday was off, and the next session because I got disconnected, or no, I don't remember. But I wrote a note and I said to myself, Tuesday, the section of 4:30, be careful with them. They have issues, like probably some gaps or some weaknesses. Then I realized after correcting your lab reports that you guys are so impressive. It's either that somebody's doing those lab reports or you're simply too serious asking and digging for answers. But you just submitted very nice lab reports. Kudos for that. I'm not done correcting. I did have the class. Yes, really 50%, not more. So far, I'm so impressed. So you guys are good. I'm not worried anymore. Just tell me when you have questions, okay? I'm gonna neglect you. So this is the conclusion. Yes, any more questions related to lab 2? All right. Our next thing on the plan is the following: linear regression. وانت أكتر وحدة كوثر, because Kawthar, you were asking me so many questions. I was worried about you, and then you gave me the most beautiful lab report. No, you're not exceptional, Roy. Many sections are really exceptional. I'm having issues correcting those lab reports. Linear regression, as you may know, we've been doing data analysis 1 and we postponed data analysis 2. This is what I want to discuss today. It's very important, okay? Very important because we need to apply it. And I forgot, oops, to do something, which is not a big deal, I suppose. All right, not in this presentation. All right, so basically, and let me keep your names next to me so I can ask you some questions. In data analysis number 2, this is the second part that we did not do and that we were supposed to do in the first week or the second week. This was the content, but I'm not gonna go over everything. What I care about for real is how to calculate the slope, because you need it in lab 3. Let me highlight. And why do we need the slope? In other words, after calculating the slope, how are we gonna use it? And eventually how to find the error on the slope, all right? Probably these 3 ideas are a bit tough, and it's okay because you will have the next lab to practice on these ideas, these objectives or skills, and you have the lab after as well to practice on those skills before the later on midterm. By the way, talking about midterms, so far I got these results with the other sections. We did not agree, this is still tentative, but I think the best day for the midterm so far is Saturday, March 20. I'm talking for 6 sections in B plus, nothing in Beirut, so we're not doing it with Beirut. The 6 sections and 2 instructors, and so far the best timing was Saturday, March 20. I was pushing for afternoon because I have an actual lab at 11 regular, and then some students were asking to move it down to 10 a.m. because they have a chemistry exam on the 22nd, and they don't want to lose all of the Saturday. At 10 on March 20. Thank you so much, Car, for informing me. Let me write it down. So you have a bio exam on March 20 at 10 a.m. So which means 4, 5, 6 p.m. is much better, right? I'm sorry for asking you to do that on a Saturday, but probably it's the best timing to make sure everybody can make it. Any other comment? Thank you, Carl, for your feedback. Anyone else? Are you okay with the date? Do you have any problem with timing? Okay, so bio on the 14th. So we're gonna delete. That's the beauty of deleting. All right, what else? Any other comments? Anyway, if you remember anything, let me know throughout the week, because this is still tentative, all right? But it's always good to give us a week or so to think about it. Back to the content. So in the first section, I'm going to discuss why a graph is a good communication tool, and I'm going to go fast on this one. Why linear relationships, I'm going to go fast on this one as well. So for the first section, I will show you some graph, random graph, just to let you know that it's very important to show a title, to label your axis, to add units to your axis, to show a very clear legend, all right? You will see some graphs. I don't know if the x-axis and the y-axis are clear. This graph looks good to me. This one is, I don't know if you find it clear or not, probably fair enough. However, the y-axis does not have a unit. I don't know what it means. This one has no title. The x-axis is not labeled, no unit. The legend is okay though. The y-axis could be acceptable. This one has no title, no labels for the axis, no units. The legends sounds cool. And this one has probably a good title. The y-axis is not labeled, and so on. So I'm trying to tell you that the graph is a communication tool, and to be able to have a good communication tool, you should be able to include a title, label your axis, add a unit, and the legend. And you can see in the comments, by the way, please check the comments on the lab report, that some of you are lacking some of these, which is okay. It was your first lab. Then linear relationships. Sometimes you plot something versus something else, and you get some points that are scattered around a certain average. And you see from the scattering that most probably the points are linear. This is linear, this is linear, and this is obviously not linear. All right, you see, it's a curve. All right, so here we're gonna discuss T versus L, and T is the period of your pendulum. So T, do you remember or do you know the period of a simple pendulum? Probably you know the period of a spring mass system. Anything? The spring mass system was 2 pi radical m over k. For the simple pendulum, it's 2 pi radical L over g, where L is the length of the pendulum, as g is the gravitational field strength. All right? Now I'm gonna ask Emilio. If Emilio is with us. Emilio, if I do plot T versus L, T versus L, do I get the linear relationship?
No.
Because
it's square root of L, so...
Yeah, so T is not proportional to L, by the way. It's proportional to radical L. And you see for a fact that if I plot T versus L in this graph, I get a curve. All right? What do you suggest we can plot to make it linear, to force it to become linear?
Either radical L or radical L over G.
All right, or probably T squared like they did here, T squared versus L. So T squared is gonna be 4 pi squared, okay, over G times L. Do you agree?
Yes, it works too.
Yeah, so if I plot this versus that, I'm gonna get a straight line passing through the origin, and you can see it. And you see the equation of the line here? This, the equation of the line. Can you tell me what the slope is?
4.0417.
Exactly. Can you tell me the units of the slope? It's the unit of y over unit of x.
So second squared over centimeter.
Exactly, that's the unit of the slope. Don't forget to add a unit for the slope. And you can, thank you so much, Emilio. And you can see something like an r squared function. This tells you how linear your function is. If you look well, and let me remove the blue line, you can see the scattering, and some points are a bit above and a bit below the straight line, right? This scattering or this tiny deviation will show you that this is a linear function, yes, with some errors. R squared will be equal to 1 if you have a super linear, like mathematically linear function, which is not the case whenever we go to physics lab or to any other lab. 0.99 means it's very close to 1, and therefore it's really amazing how linear it is, or how small the deviation from the best fit line is. This is another example that would show you the equation of the straight line. Probably I can ask Romy. Romy, what is the equation according to the yellow answer? Or tell me the slope.
The slope is 2.5.
The unit of the slope is?
Grams.
You can say grams. Yes.
Number, y over x, grams per number of crackers.
Exactly. By the way, just remind me to save as this presentation so I can send it to you. All right. Okay, so yes, this is exactly, thank you so much, Romy. Now I'm gonna check this one. These are 4 examples. They give you the equations and they give you the R squared function. You see the R squared value, it's 0.98, 0.86. This is very small and you can see the deviation. This is 0.99, this is 0.96, and for a fact you can see a deviation, you know. You always have a deviation. The bigger the deviation, the farther the R squared value from 1. What about this one? I can ask Chloe. Chloe, if you look at your measurements, do you think that this can be considered linear?
So definitely not.
Obviously not. So, and you see the R squared function, this is the R. If I do R squared, I will end up with 0.1 something. This is far away from 1. So the fuel used versus speed, they're not proportional. Nothing is linear. It's really, we cannot do linear regression when you have something like that. All right, now item 3, how do we calculate the slope? I know for a fact that you usually take 2 points on the line. You do rise over run or y2 minus 1 over x2 minus x1. Please do not do this anymore. We only do this if we have 2 points on the line, right? However, if you are given points like these, none of the points are on the line. And to be honest, you don't know where the line is. The line does not exist yet. Your job is to find the line. To find the line, you need to find the slope, the y-intercept, and write the equation. You see? So if you don't have the line, you don't have the equation, how can you take 2 points on the line? That's why we do not want you to do this, okay? Keep that in case only you are given the line. We have 2 methods. We can use Excel, and I'm gonna show you it so quick. You put the values, you select them, you insert scatter, and you write the equation. It takes 1 second. Or you can use your calculator. I will send you a link of a video I did myself on my own calculator. Yes, Mashi, I put the values of x and y, click linear regression, find slope. It's also very quick, but I thought since we will be allowed, the exam is gonna be computer-based if we will go on campus or not. So why not do it on Excel? Excel is has a very good display. So no need to learn both methods, it's up to you. My job is to deliver both methods for you, all right? Let me open Excel and show you one demonstration because you need to do this in your lab number 3. So we're not wasting time. We need that for lab 3. I'm gonna give you X and Y. I'm gonna give you randomly 1, 2, 3, 4, 5, and then 10, 20. Forgive me, I just picked a very super linear function that is mathematically acceptable and experimentally not possible. Yes, actually you learn a lot in biostats, and I believe biostats will actually teach you so many interesting and important stuff. I wish I ever took biostat in my, I don't want to say childhood, I don't want to make you kids, but yes, I think it's a very interesting course. So I'm gonna write X first and Y first and Y second. I put the label X and Y only for myself, for me not to be confused. I'm gonna select them, insert, scatter. I'm gonna pick this one without any line. Change the title, add the axis label and units or whatever, you're good in that. Then I'm gonna do right click, add trend line. Trend line means best fit line. And the best fit line here can be linear, exponential, polynomial, anything you want. We're gonna pick linear, and then we're gonna say display equation and display the R squared value. All right. When did you manage to take biostatics? Was it in the fall? You're lucky. I'm gonna change the font a bit so you can see what I did. So the equation of the line, probably I can ask Marianne. Marianne, what is the equation of the line? Or what is the slope? Marianne is here? No? Jana? All right, yes. Can you look at the example I did, Marianne? What is the slope in our case? 10x plus 0. What's the slope? Anyone else? Karen? Okay, 10. Yes, exactly. So 10 is the slope. I don't have any units in here because x and y were not given units. My bad. You see the r squared function is equal to 1 because r squared value, because this is super linear. Now I'm going to change this to 11, this to 22, this to 28. And you can see the points are actually deviating a bit. This is 42. And this is 55. I was surprised to see that this did not change. What I'm gonna do is I'm gonna right click and add equation again. So what I did, I removed the equation and I'm gonna put a new equation, and you will see that it's gonna be a bit different. So the slope has changed and the r squared value has changed a bit to show you that you actually have a deviation from the best fit line that would deviate your r squared value away from 1. All right. So as you see, it took me nothing to do this, to find the slope or to write the equation of the straight line and to plot, like I did everything in one shot. So back to our presentation. This is another example that was supposed to be an assignment, and I've hidden the solution. You were supposed to plot u versus I, Ohm's law. So the slope is gonna be r. So the question is, use Excel to find the slope and use the calculator as well. We're not gonna do that because we're gonna do lab 3, which is also a very good application. Now, why do we need the slope? I will ask Dalal to help me. Dalal, this is Newton's second law. M is the mass of my system and it's constant. All right. I'm gonna plot F versus A. What does, my first question is, do you expect a linear relationship, Dalal?
Yes.
All right, because obviously F and A are proportional. Now that the relationship is linear, what does the slope represent?
The slope represents M.
Well done. Another question, if I plot A versus F, what does the slope represent?
1 over M.
Awesome. All right, stay with me. If I plot U versus I or I versus U, what do I get? Linear or not?
Also linear.
All right, what does the slope represent?
R.
It's 1 over R, right? Because I have U equals Ri, yes. So I is 1 over R times U. Let's say, all right, they're fixing the house again. Let's say that F is a constant and I want to plot M versus A. Do you get a linear relationship?
No.
All right, how does it look like? And why not?
No, we got a linear relationship.
All right, do you think M and A are proportional?
If.
So the heavier the object, the smaller the acceleration. You know this. They're inversely proportional. They are inversely proportional. If you want, we can write M to be equal to 1 over F. No, it's equal to f divided by a, all right? Which looks like y is equal to constant over x. So obviously this is not an equation of a straight line, this is a hyperbola. And hyperbola will give you the function inversely related, like inversely proportional, okay?
Okay.
All right, thank you so much. Now for this example, we already discussed it, but we never discussed what the slope represents. Probably I can ask Christopher. Christopher, if I plot t squared versus L, and I do get a linear relationship, but yes, what do you think the slope represents? Let me see if I can zoom in. Christopher is not here. Probably Roy can take over. So the question is again, Roy, I'm plotting t squared versus L. What does the slope represent? Probably I can take this slide because we have more space. So if I plot t squared versus L, I want to know the slope. Would it be mass? Would it be, I don't know, radius? Would it be resistance? Would it be force? Would it be acceleration? What is the slope? Anyone else? Probably the girls are good in this.
Is it L?
All right, so again, I'm plotting.
Is it 4 pi squared over g?
Exactly. This is y, this is x, therefore this is the slope. So yes, the slope is 4 pi squared over g. That's so true, Jana and Kausar and Christopher. No, I couldn't hear you. By the way, who just answered? Is it you, Roy?
Yes.
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 All right, thank you so much. So now we're gonna start with error on the slope. Let me check the time. We're good enough. So we're gonna plot. You see now all these points are on one line and the error is so small. In this example, you see a lot of scattering, right? And if I find the best fit, you see all the points, they are deviated from the best fit line. So I can think of average and standard deviation in here, right? All right, I'm gonna learn how to find the vertical deviation. And I'm gonna find the vertical deviation for each and every measurement I'm gonna do. I know it's a lot to do. You see here, the vertical deviation is so much smaller. So the error on the slope here is smaller, obviously, because the points are not scattered a lot. Okay? So I'm gonna learn how to find the deviation between the actual measurement and the actual line. This is the measurement. It has a y, like the ordinate, and the line has a y equals to bx plus a, or mx plus a, or mx plus b, whatever you wanna call it. All right, the equation of the straight line. So you're gonna take the ordinate of the point and the equation of the line. You already have the y-intercept and the slope, and you're gonna do minus. You're gonna find the deviation for this measurement, deviation for this measurement, all the deviations. You're gonna square each and then you're gonna add them all, exactly like we do the RMS error for an average. But this is RMS two-dimensional. I have an x-axis and a y-axis, okay? How do we calculate the error on the slope? I will send you a video of myself doing the calculations on a paper, but not really on a paper, on an Excel spreadsheet, using this equation. What is n? N is the number of points, measurements. What is EI squared? E1 is the ordinate of the first measurement minus the y value of the straight line. So it's gonna be ax1 plus b, or bx plus a, whatever. I mean slope x plus y-intercept. So this is the straight line, and this is the actual point which is deviated, and the minus is the vertical deviation. I'm gonna do E1, E2, E3, and so on, and then I'm gonna square each, and then I'm gonna do sigma, which means I'm gonna add them all. But I'm not gonna do this by hand on a calculator. It's very easy to find y squared. All right, let me make sure the font is visible to you. To be able to do y squared, I do equal this squared, and I'm gonna drag. So please don't do the calculations by hand, I mean one by one. You do one and you drag. And if you want to find the sum, you do this and you click sum, which is here. Okay, this is the sum. Done. It took me 2 seconds. Squared, then sum. Let's say I want to find the sum of this one. I do sum. And let's say I want to find the square of this value. I start with equal and then do square. Probably you know this. Probably you don't, all right? A lot of my students don't know they can do a lot of, and I can call this an Excel spreadsheet. You can take a screenshot like this and insert in your document by showing me any calculation you want. You can have a nice table, label it, you know, for you to include it in a lab report and to make it complete anyway. So for you to find delta, I mean the error on the slope, you can easily on an Excel spreadsheet do all the calculations needed. What is delta, which is here? Delta is given by this equation, and n is the number of points. Sigma xi squared means you square each x, then you add. Here you add all the x's, then you square them. And you end up with an answer, one answer that you include here. When you're done, don't forget to do radical answer, and don't forget the 3 conditions. The error must be 1 sig fig, it should have a unit, and you should round the slope accordingly, okay? I know this is tough. It could be new to you. Probably you did not do that in biostat, I don't know. All in all, we're gonna have our lab 3 as a practice, and let me know if you're having difficulty. Probably the video is gonna help you. By the way, I forgot to tell my other students, there's something called the linest function. I don't want us to discuss it today. The linest function is a function on Excel that can give you the error on the slope very quickly. I will share with you a link explaining how to do it. It's up to you to learn to do that now, or probably after the midterm, you can think about it. All right? It's just another method to find the error on the slope. And that was an assignment simply to tell you, to help you practice, but we don't need to do it. And let me check, Kausar, do we have an error on delta? What do you mean delta this? Delta is a component inside the equation. So it's, instead of me writing n sigma xi squared minus a sigma xi squared, all of it squared, instead of writing it here, I wrote random value beta, and then I wrote beta alone. So no, delta means nothing. It has no meaning whatsoever. It's only to reduce a big equation that looks awkward into a tinier one, that's all. All right, so I'm gonna save this, keep it with you, for you. I'm gonna open a new folder called Data Analysis 2, and I'm gonna throw all the links that you need in it. Now we can start lab 2. I just realized that, I'm gonna stop sharing for a moment. I realized that the lab number 2 that I have is annotated. Actually, I saved on the original copy. I need a 1 second to delete everything because I want to test you. I mean, I should ask you a lot of questions. I need 1 second just to empty some important slides. What did I just do? I just did something. All right, let me save again, close. Okay, I need 1 second. Okay. I usually save as, and I did not save as. I'm not gonna change a lot, only the main stuff I need to hide. Otherwise, and that's it. All right, now I'm gonna share, it's like I'm hiding something from you. Okay, now I'm gonna share again. Back to the presentation, our lab 3. Are you guys ready? So I'm gonna follow the same scheme, I mean an outline. That would be, what is the general definition of acceleration? And then I'm gonna say, what's the difference between centripetal and tangential acceleration? This is something grade 11 material. Then I'm gonna discuss Newton's second law to find the centripetal force. We discussed our experimental setup, and eventually this analyzing your data, I mean what we need as data analysis for our lab. All right. Question number 1 is, and let me save as for me not to do the same mistake again. And this is Centripetal force 3. 3 is your section. I want someone, anyone, everyone to give me a good definition of acceleration. What is an acceleration? It's a very simple term, and these are your names. Yes. How do you define acceleration? Anything.
It's how much, if we're taking the example of a cart, it's how much the cart will speed up every second.
All right. Speed up every second. So you're saying if the cart is not speeding up, there's no acceleration.
No, it can be negative. It's how much the velocity is changing every second.
This sounds so much better. Kausar is saying change in velocity. I like this. However, Kausar, be careful because change in velocity is in meter per second and the acceleration is meter per second squared. Karan is saying difference in velocities during a specific amount of time. What do you mean by difference? Is it something minus something, like magnitude minus magnitude? Be careful because the magnitude of the velocity may not change, and yes, you can still have acceleration. Christopher is saying the derivative of v with respect to time, and I like this. However, probably we should stress on the fact that v is a vector, change of velocity over time, change in speed over time, rate of change of the velocity with respect to time. Okay, how about we come up with an actual something to say? I would want to keep the rate at which velocity is changing, just to make it a bit general, okay? And by velocity is changing, I'm talking about the velocity, and you're gonna tell me the definition of velocity in a moment. The rate at which, rate means divided by time. So the idea of rate, it means over time. So no need to say the rate at which and then say over time. All right, now I need someone or everyone to tell me how you define velocity. So we're done with acceleration. How do you define velocity? Anyone? Velocity. dx over dt. What about if it's y or x and y? Change of position. All right, change of position is gonna be in meters and velocity is meter per second. The rate at which displacement is changing, I like this. Distance traveled per second, distance or displacement, the rate at which position changes over time, speed. All right, anyone can tell me the difference between speed and velocity? Is there any difference or not? There is a difference, Kausar. What is the difference? Okay, direction. Can I say that velocity, all right, velocity, come on. Velocity is equal to speed plus direction? Can we say that? So speed depends on position, velocity on displacement, speed. So we say speed is distance over time and velocity is displacement over time. The speed is the magnitude of the velocity, yes, and we add a direction to it. All right. So now we have all the picture we need, everything we need. The acceleration is the rate at which velocity is changing. So if the speed is gonna change, I have acceleration. And if the direction is gonna change, I also have an acceleration. So speed changes and or direction changes, I will have an acceleration. So now I'm gonna discuss the centripetal acceleration and the tangential acceleration. A tangential means it's tangent to my motion. It speeds me up or slows me down. And to find it, we're gonna do V final minus V initial over time. And again, or you can do dV over dt if the change is not linear, definitely. By V, I mean the magnitude of the velocity and therefore the speed. So what's centripetal acceleration? It's an acceleration directed towards the center of my motion. Some people call it the normal acceleration because it's perpendicular, because anything directed to the center means going to the radius, and the radius is perpendicular to the tangent. So it ends up being perpendicular as well. And to find the centripetal acceleration, we do V squared over R. V squared is the speed again, at a certain position, and r is the radius. The faster you go, the more acceleration you feel when you turn, and the smaller the radius, the more acceleration you feel when you turn. Okay, so now we have to think of two accelerations separately. One to speed you up, slow you down, and one to turn you. Now I'm gonna use Newton's second law to find the centripetal force. I'm gonna say net force is equal to ma. I'm gonna break down the vector net force into a tangential and a centripetal component. The centripetal component is gonna be MAC. Right, be careful, the centripetal force is not one force called centripetal force. It's the resultant of all the forces that are in the centripetal direction. It's as if I'm saying sigma Fx, or the net force along the x-axis. So centripetal force is the net force along the centripetal axis, okay? It could be the tension in a wire, it could be the resultant of the normal to the mg in an inclined plane. Like, you know, normal and mg cos will cancel, so you'll have mg sin. So it is a resultant that is in the centripetal direction. I'm gonna replace a by v squared over r. So I'm gonna have m v squared over r. All right, this is very general. Examples. This is a satellite. The only force on the satellite is the force of gravity. The force of gravity is directed towards the center of the circle, of the motion, of the orbit. It is a centripetal force. Here, the girl is spinning a ball on a string. So the tension of the string will be, the tension in the spring will be the centripetal force. The centripetal force is the resultant of the weight and the normal. Obviously, the normal is a little bit smaller than the weight for the centripetal force to be downward, and so on. I believe this is a very interesting example. I wish I would give you more of this, but the centripetal force here is a mixture of friction, and if the road is not horizontal, sometimes it has a certain angle, you have mg sin, because mg cos and the normal are gonna cancel out. So mg sin along with the friction would help the car to go in a circle, all right? Yes, there's a cross-sectional figure that I believe is very interesting. But anyway, in this example, I'm trying to show you that the centripetal force is not an actual force. It is any force or any resultant of two forces. Now our setup. You will see a real picture of the setup from PASCO. So I took this from the PASCO website, and this is a diagram from the lab report, from the manual. So what do you understand by this? All right, so basically you have a stand. Where is my pen? You have a stand and you have a rod. On the rod, you have a platform that can rotate. I'm gonna show you in the video. It's a very fast rotating platform. Friction is reduced. It's very similar to the track of the motion on an incline. It is aluminum. It is graduated with a regular ruler. It turns so fast. You have the center post. Center post means that it is at the center of the rotating platform. On the center post, you have a spring and a wire. In other words, the spring is gonna be elongated and there's a lot of tension in it. It's gonna pull this mass in a certain direction. Let me zoom in. You have a pulley here, and around the pulley you have a wire. All right, let me change the thickness of my pen. All right, this is my system, and you will be confused with which is your system. Be careful, this is your system, and I'm gonna stress on this part. The mass of which is 200 grams, and don't worry, I'm gonna give you this value again. Your system is attached by many wires, 3 wires actually. 1 wire attaching it here, 1 wire attaching it to the spring that is elongated and therefore that presents a lot of tension, pulling the object in this direction. And here you have another force, which is the weight of the hanging mass. I'm gonna call it small m, so the system is gonna be big M, and all the students were confused between small m and big M. And this weight is gonna pull the system in this direction. This wire is not gonna pull the system. It's gonna only leave it at a certain position, not allowing it to fall down. All right? My question for Omar is, Omar, are you there?
Yes.
All right, so Omar, my question for you is the following. What happens if I remove the hanging weight?
It goes to the right.
Yeah, the system is gonna move a bit to the right. All right? Okay, now I'm gonna remove the hanging weight and I'm gonna remove the pulley. The system is gonna move to the right and I'm gonna rotate the platform. When I rotate the platform, do you think my system is gonna stay as is or move out or move in?
Move out.
Yes, it's gonna move out. I'm gonna keep on rotating it, increasing the speed for my system to go back to the same initial position. I will say that the centripetal force of rotation is similar to the hanging weight. All right, this is very difficult for some students to understand. Let me explain again. When you will put, and I have a feeling I'm gonna sneeze, when I will put a hanging weight on my system, I will make sure that all the wires are horizontal and vertical. I'm gonna create the perfect alignment by changing the length of the wire and so on. This wire has to be horizontal, this is horizontal, this is vertical. And then I'm gonna remove the hanging weight, remove the pulley and start the rotation. The system is gonna move at a certain speed. I will increase the speed until the system go back to the same position. And when the system go back to the same position, I will say the centripetal force is equivalent to the hanging weight because it mimics the same behavior. Is that too difficult to understand? So the centripetal force will be equivalent in magnitude to the hanging weight if the system will go back to the same initial position, right? This is a bit tough. I can repeat it definitely. Now, the tough question is the following, and probably let's discuss it here on this figure. So you see, we removed the wire. It's no more there. That's why the system went a bit to this position. This is not super horizontal. So I should have this a bit longer to have the best alignment. This pulley is high. By the way, I can rotate the pulley a bit down to have a horizontal wire. So before I start the experiment, I should make sure this wire horizontal, and this is vertical. You can adjust by changing the length of the wire and it takes time. You're so lucky, I'm gonna do it for you. And then I'm gonna remove the pulley because I want my system to be symmetrical. By the way, those masses are not there. It's just a symmetrical system, minus this because this is not symmetry. Anyway, I'm gonna remove everything. This is gonna go a bit in this position. I'm gonna start rotating. I will put my hand here for rotation to be smooth. Everything is gonna rotate and this is gonna move a bit far. Whenever it reaches the same initial position, I'm gonna say this is the speed at which the centripetal force is equivalent to the hanging weight. I'm repeating, I know. Now, how do I know I reached the exact same position? There's something here that is very interesting. You have a red, what do I call it? A red, it has a name. A red, anyway, no problem. It's a red disc to show me where the spring is when I have alignment. So when I have a perfect alignment, I'm gonna make sure the red disc is inside the transparent ring. By the way, I can move the ring up for the red ring to be inside the transparent ring. All right? When you remove this mass, the red, it has a name, the red something is gonna move up because the system is gonna move to the right. Very simple. When rotation will start, the system is gonna move slowly back to its position. And whenever the red ring goes back to its position, I would know this is the speed that is needed. So if the red ring is a bit above the transparent position or a bit below the transparent position, I would know I'm too fast or too slow. Whenever I reach the red ring to be inside this empty ring, it means that my system is back to its initial position, okay? It's experimental and I'm doing it by hand. So I'm gonna rotate too fast, too slow, to make sure I reach the speed needed that would give me the centripetal force needed. Okay? Now my question for Maria is, Maria, as I'm rotating the platform, I need to find the speed of my rotating platform. And to be able to do so, I'm gonna do distance over time. Can you tell me what is the distance covered by the rotating platform during one circle?
2 pi r.
Thank you so much. The other group, they didn't know. So 2 pi r is the circumference, and during one revolution, it's gonna go a distance of 2 pi r.
A period.
Yes.
T.
And I'm gonna call the time needed for one revolution to be a period. Maria, how do you measure the period? Using which measuring tool?
A timer.
A timer.
It's a time.
It took them 5 minutes to tell me a timer. Any stopwatch, your phone actually has a digital stopwatch. And to be honest, all the stopwatches I'm encountering, your phone, iPhone, or Samsung, or whatever digital stopwatch we have in the lab, they would give you 2 decimals second digital measuring tool. All right, I'm gonna time. Another question for you, Maria, and so far you're impressing me. What will you do to measure the period if the period is so small? Like it's too fast. How can you measure a period?
If we have a number of revolutions, مثلا 1 in 1 minute or so, we can find the frequency and 1 over f is t.
So bright. Did you do this lab before? Are you cheating?
No, I just took this in physics.
All right. So we're gonna measure the time taken through many revolutions, let's say 5 or 10, and then find the period by dividing by 5 or 10. Very simple, because it's not smart to measure the time for one revolution. If it's too fast, it's gonna be not accurate at all. So we usually measure the time through many revolutions, okay? So before I show you the lab report, which is here, let me show you a bit the experiment. And by the way, I deleted the video, my mistake, and I cannot find it in the trash, but I have 2 videos that I used to stitch, and we have the link on YouTube, so no worries. I'm gonna go fast forward. This is what you have. The video is not great, but I couldn't take another video. I will try to go on campus to take another video. Why isn't it moving? Oh, here I'm talking, that's why. I'm gonna explain a bit how I will do the alignment. So this is the central post, this is the side post. You see the system, there you have some wires. I think I stopped the video to create a node with the wire because it was too long or too short. I'm explaining, by the way, do you see the spring here with the red ring? And you have here a black, what do I call it? A black ring, you know, the red would go inside the black. The black can be moved up and down. I'm gonna show you how, whenever you create equilibrium and alignment, for you to remember where the position of the system is. So here I'm showing you the wires. I'm gonna explain how the spring can be elongated, how it goes around the pulley, how the system is attached to 3 wires, and eventually that the 3rd wire is attached to the system, goes around the pulley, and you see I'm gonna add some extra masses to my hanging weight. All right, then I'm gonna show you nothing. Here in the 2nd video, I think all right, so here I already have the wire ready, but you see this is not aligned. It's not vertical. I will change a bit the length of the wires. Okay, add some extra hanging weight or anything I want. By the way, do you see the red ring and the black ring? Okay, so I'm gonna create a perfect alignment. I think this is a perfect alignment, vertical, horizontal, horizontal, although you cannot see the wires well. Now I should move the black ring to the red, that I cannot remember the name. Okay, look, the black can be moved. You see how I'm moving the black? So the black can be moved up to remember where the red ring was. Okay, all right, now I'm gonna remove the hanging weight and you will see that the hanging weight is moved. Okay, it's here in my hand, and this moved a bit in this direction, not a lot, because you see the red ring moved a bit up few millimeters, but I'm gonna do the experiment again with greater centripetal force. And here I'm rotating the platform. How am I rotating the platform? Do you see my hand on the rod? If the rotation is too slow, the red ring is gonna be above the black level. If I'm moving so fast, the red ring is gonna be below. I'm gonna move with a certain speed that is good enough to reach the black level, all right? Because the black level is what I want to reach, okay? So I'm rotating again using my hand, and with a different hand, I can use a timer to do the measurements. All right, I think here I'm gonna repeat the experiment by changing the radius. I just moved, you see, the gray post. I did the experiment again. I'm using the same hanging weight. I created an alignment by having a longer wire. And then I'm gonna move the black post, the black level to the reds. Let me see if I did it. You see how much the spring was elongated? Now I'm gonna, you see, I moved the black down to the orange indicator. Orange indicator, this is the name of it. All right, then I'm gonna remove the hanging weight. Obviously, the orange indicator is gonna move back up because there's no more hanging weight. I'm gonna start rotation. If it's too fast, the orange indicator will be below the black ring. If it's too slow, it's gonna be above. So I'm gonna be so skillful that I should create rotations that are not too fast, not too slow, for the orange indicator to be inside the black ring. You see? All right. Sometimes it's gonna oscillate a bit up, a bit down. As long as the average is on the black indicator, it's gonna be okay. Fine. So this is what is being done. Usually the students find it a bit difficult to understand how this actual speed would give me a centripetal force that would mimic the behavior of the hanging weight, like be equivalent. All right, so now you're gonna change the radius. For each radius, you're gonna measure the time and then the period. All right, now let me discuss a bit the equation. Don't you have that the centripetal force is equal to mv squared over r? And with the help of Maria, we wrote that v, let me go back to a thick pen. We wrote that v is 2 pi r over period. Okay, if you plug in 2 pi r over period in the place of v, you will end up with an equation that would give you r to be proportional to period squared. Okay, I need to remind you that this is the mass of your system, big M, and this is the weight of the hanging mass, which is small m times g. All right, so you plot r versus t squared, you get a straight line passing through the origin. You do linear regression as I told you, using Excel or any other platform, and the slope is gonna be related to the centripetal force, and obviously the mass, and obviously 4 pi squared, and so on. So plot radius versus square of period, y versus x. Draw the best fit line. Excel can do it for you. Find the slope. Excel will give you the equation. You take the slope. The error on the slope. Take your time. Don't be frustrated. It's your chance to learn how to do the error on the slope. Then they want you to deduce from the slope the centripetal force. So write the equation again as r equals something t squared. The something is the slope. Now inside the something you have the centripetal force. The centripetal force is gonna be slope times something over something, all right? And then you need to find the error on the centripetal force by doing propagation of error, because you have an equation and all the items, there's an error on every item. Then you compare the value of the centripetal force you got to the value of the centripetal force experimental, which is your hanging weight. And you list some possible sources of errors. How do you know the sources of errors? You can look at the video, probably the setup, check what's horizontal, what's not, if the alignment is perfect or not. You can check, for example, the measuring tools. Some of them are not very precise. All measuring tools they have a limited precision. You can think of human error while timing. Sometimes I need to stop timing, but I have a slow reaction time. 3 sources of errors are enough, but we can easily name 6. All right, you can name more than 3, but 3 minimum. All right, so I believe that's it. I'm gonna send you the PowerPoint and the video and some results. I already did that with your friends, and we fine-tuned the results a bit to reduce the percentage error. And let me show you the lab report. This is a sample of results. You're gonna be given the mass of the system, and I'm gonna stress that this is the system. This is the mass of the hanging weight, grams, and this is the radius. You can tell the error. I'm using a regular ruler. The timer, I'm using a digital measuring tool. The period, by the way, you can see here, yes, not here in the procedure, they say to time 10 revolutions. Yani it's gonna rotate 10 times to time. So for you to be able to find the period, you divide by 10 and then t squared. And I don't see that they want the error on period and period squared. All right, that's it. Questions? Are we done? Any question? I'm sorry, I've been talking for a long time. All right, I'm gonna stop recording. I'm gonna stay behind a bit.